Metallographic sample preparation of traditional forging knife embryo. Forging knife embryos look ordinary, but in ancient times, it was a core tool that supported human survival, production, and life. A traditional forging knife, hidden in the sound of the hammer, is the survival wisdom of the ancients. Regional folk customs are engraved in the lines. 1,000 trials and tribulations are both witnesses to past lives. It is also the link that continues the traditional culture today. What kind of process code is hidden inside it? Today, we use metallographic slices for a physical examination across the millennium. Cutting. We cut and sample using CT250 manual metallographic cutting machine with alumina grinding wheel cutting blade. Representative samples were cut from the middle of knife embryo. The cutting process requires sufficient cooling. Avoid heat-affected zone interference with original tissue. Mounting. The cut sample is secured with a metal clamp to prevent displacement during inlay. Then hot press inlay machine. Place the sample into the sleeve. Add normal hot inlay under high temperature and pressure. Made into a standard cylindrical sample with a diameter of 30 mm. Inlay is not only convenient for subsequent grinding and polishing, it also protects the edge. Grinding and polishing. The purpose is to remove the damaged layer step by step through grinding and polishing steps. Step 1. P400 silicon carbide sandpaper to quickly smooth the surface of the sample. Eliminate macro damage caused by cutting. Step 2. Pause grinding and polishing plate. With 9-micron polycrystalline diamond polishing liquid, remove coarse abrasion marks and initially reduce the deformation layer. Step 3. SC polishing cloth with 3-micron polycrystalline diamond polishing solution. Further refine the surface to eliminate minor scratches. Step 4. ZN polishing cloth with 50 nanometers silica polishing liquid final fine polishing. Remove residual stress and fine scratches to obtain a non-deforming mirror surface. Corrosion and observation. Corrosion of samples with 4% nitric acid alcohol for 5 to 10 seconds. When the surface color turns matte gray, rinse and dry immediately. The prepared sample is placed under a metallographic microscope. Knife back. Slow cooling. Retain normalized pearlite. Good toughness but low hardness. Transition zone, pearlite and martensite mixing. Due to uneven quenching and cooling. Blade core. All martensite should give ultra-high hardness, but weakened by residual austenite and inclusions. In addition, fold forging joints. It can be seen that the slag formed by the embedding of the oxide scale and local decarburization due to high temperature exposure. Hard martensite cannot be formed during quenching in the decarburization zone according to the C-curve. Only pearlite can be generated, which becomes the weakness of the blade. If there is oxidation and decarburization at the edge, a pearlite soft layer will be formed after quenching. Subsequent cutting must be completely removed to expose high-carbon martensite. Only then can it be guaranteed to be sharp and wear-resistant. This microscopic exploration has allowed the quantification of the internal tissue state of a traditional broken knife become a living textbook for materials science, technology, organization, and performance chain. Through this tiny world, we see clearly the glory and shortcomings of traditional forging knives. Metallographic analysis is the key bridge between millennia-old techniques and modern science. Let every drop of sweat lead to a more extreme edge.
Trojan. Discover the truth of material.